Happy 30-2s. We're going to look at lesson 6.3, solving exponential equations. So look in your notes and make sure you guys are on lesson 6.3, exponential equations. So that should be on page number 12 for you guys. Okay, so in your yellow booklet, 6.3. So I'm going to tell you a little story that's going to be relevant to this first question that we're going to do. So take a look at this.
One Grain of Rice by Demi, a mathematical folk tale. Long ago in India, there lived a Raja who believed that he was wise and fair, as a Raja should be. The people in his province were rice farmers. The Raja decreed that everyone must give nearly all of their rice to him. I will store the rice safely, the Raja promised the people, so that in time of famine everyone will have rice to eat and no one will go hungry. Each year, the rice collectors gathered nearly all of the people's rice and carried it away to the royal storehouses. For many years the rice grew well. The people gave nearly all of their rice to the Raja and the storehouses were always full. But the people were left with only just enough rice to get by. Then one year the rice grew badly and there was a famine and hunger. The people had no rice to give to the Raja and they had no rice to eat. The Raja's ministers implored him, "Your Highness, let us open the royal storehouses and give the rice to the people as you promised." "No," cried the Raja. "How do I know how long the famine may last? I must have the rice for myself. Promise or no promise, a Raja must not go hungry." Time went on and the people grew more and more hungry, but the Raja would not give out the rice. One day the Raja ordered a feast for himself and his court, as it seemed to him a Raja should now and then, even when there is famine. A servant led an elephant from a royal storehouse to the palace, carrying 2 baskets full of rice. A village girl named Rani saw that a trickle of rice was falling from one of the baskets. Quickly she jumped up and walked along beside the elephant, catching the falling rice in her skirt. She was clever and she began to make a plan. At the palace, a guard cried, "Halt, thief! Where are you going with that rice?" "I am not a thief," Rani replied. "This rice fell from one of the baskets and I am returning it now to the Raja." When the Raja heard about Rani's good deed, he asked his ministers to bring her before him. "I wish to reward you for returning what belongs to me," the Raja said to Rani. "Ask me for anything and you shall have it." "Your Highness," said Rani, "I do not deserve any reward at all, but if you wish, you may give me 1 grain of rice." "Only 1 grain of rice?" exclaimed the Raja. "Surely you will allow me to reward you more plentifully, as a Raja should." "Very well," said Rani. "If it pleases your Highness, you may reward me in this way. Today you will give me a single grain of rice. Then, each day for 30 days, you will give me double the rice you gave me the day before. Thus, tomorrow you will give me 2 grains of rice. The next day, 4 grains of rice, and so on for 30 days. "This seems still to be a modest reward," said the Raja, "but you shall have it." And Rani was presented with a single grain of rice. The next day, Rani was presented with 2 grains of rice, and the following day, Rani was presented with 4 grains of rice. On the 9th day, Rani was presented with 256 grains of rice. She had received in all 511 grains of rice, only enough for a small handful. "This girl is honest, but not very clever," thought the Raja. "She would have gained more rice by keeping what fell into her skirt." On the 12th day, Rani received 2,048 grains of rice, about 4 handfuls. On the 13th day, she received 4,096 grains of rice, enough to fill a bowl. On the 16th day, Rani was presented with a bag containing 32,000 768 grains of rice. Altogether, she had enough rice for 2 full bags. This doubling adds up to more rice than I expected, thought the Rajah, but surely her reward won't amount to much more. On the 20th day, Rani was presented with 16 more bags filled with rice. On the 21st day, she received 1,048,576 grains of rice, enough to fill a basket. On the 24th day, Rani was presented with 8,388,608 grains of rice, enough to fill 8 baskets, which were carried to her by 8 royal deer. On the 27th day, 32 Brahma bulls were needed to deliver 64 baskets of rice. The Rajah was deeply troubled. 1 grain of rice has grown very great indeed, he thought, but I shall fulfill the reward to the end, as a Rajah should. On the 29th day, Rani was presented with the contents of 2 royal storehouses. On the 30th and final day, 256 elephants crossed the province, carrying the contents of the last 4 royal storehouses, 536,870,912 grains of rice. Altogether, Rani had received more than 1 billion grains of rice. The Rajah had no more rice to give. "And what will you do with this rice?" said the Rajah with a sigh, "now that I have none?" "I shall give it to all the hungry people," said Rani, "and I shall leave a basket of rice for you too, if you promise from now on to take only as much rice as you need." "I promise," said the Rajah. And for the rest of his days, the Rajah was truly wise and fair, as a Rajah should be.
I love that story. So it's a good story because it shows you exponential growth in practice. So it's similar to this one. So there was a person that made a chessboard, and the king was so pleased with his chessboard, he asked, "How can I pay you?" And this is what the fable says. It says that the person wanted to be paid with 1 grain of rice on the first square, 2 grains of rice on the second square, 4 grains on the third, and so on, until all 64 squares on a chessboard were covered. So we want to figure out what this would be as an equation. So they're giving us the equation y equals ab x minus 1. In our previous lesson, we should have found that the a value is our y-intercept. So that means how much grains of rice do you initially get? Initially, meaning at the beginning, how many grains of rice do you have? So initially what happens is that the person is given 1 grain of rice. So we would say y equals a is 1. B represents your base. So what is happening to take you from one square to the next? So remember that you're getting 1 grain of rice on the first day or first spot on the chessboard. Then you're getting 2 grains of rice, then 4, then 8, and so on. So what are you doing to go from number to number? So you should always see that it's multiplying, or it should be multiplying by a whole number or a fraction to go from one to the next. This one is multiplying by 2. So this is doubling. This is by a factor of 2. And then the x minus 1 stays as it is. So you should always in an equation have an x and a y. So that's our equation that we're going to be using to solve for this. Remember, x is going to represent what square you're on the chessboard. Square number on chessboard. Versus y will represent the number of grains of rice that you have. So the number of grains of rice that you have on that square itself. Okay, so on that square, how many grains of rice are you getting? So determine how many grains of rice correspond to square 44. So remember, our square number represents x. So we're given that x is 44. So we're going to plug it into the equation. Y equals 1, 2, to the power of, instead of x, we're going to replace it with 44 and then take away 1. So we're going to start by simplifying this. So y equals 1 multiplied by anything does not change the value. So we can omit this. We do not need to write the 1 because 1 does not affect the answer. So we're just going to have the base to the power of 44 take away 1. 44 take away 1 is 43. So what we'll do is we'll go to our calculator and we'll put 2 to the power of 43 in our calculator. Okay, so in our calculator, you should be putting 2 to the power of 43. Okay, so there's my power button. Guys, there's my power button. Equals, and it's quite large. So this is 8.79 times 10 to the power of 12. So I'm going to write out the number so you guys can see what it really looks like. So the actual number that you should be writing is, you have 8 and the decimal spot is here, but what we're going to do is we're going to move the decimal spot 12 spots to the right. Okay, so we're going to go 8, then we have 1 decimal spot, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So what I did was I moved the decimal spot from here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's what the real number actually is. So this is how many grains of rice they're going to get on the 44th square. Therefore, they will get this many grains of rice on the 44th square. So that's what we just found by using the equation. The next question, B, determine the square on the chessboard that would correspond to 128 grains of rice. So in this case, they're giving us, if you look back to our first part where we talked about grains of rice, is y. Y is equal to 128. So they're telling us what y is, and they're asking us what square are you on. Okay, so what we're going to do is we're going to write the equation out. Our equation was 1 times 2 to the power of x minus 1. And instead of replacing a y here, we're going to put in the y spot 128. Okay, so this is our equation that we're going to solve for. Okay, so the next thing is, what I want to do first is I want to get the base and the power by itself. So what we're going to do is we're going to divide this number and this number, this number and this number by 1. So we're going to divide out this 1 to both sides. So we're going to divide the right side and the left side by 1. So you'll see that those do not change the answer. So by dividing out 1, the 1's cancel, and 128 divided by 1 is still 128. Next, we're going to use something called common base method. So I'm going to show you what to do there. So we have to think of 2 to the power of something. So we're looking at this number right here, 128, and we're saying 2 to the power of what number replaces 128. So in your calculator, I want you guys to put in 2 to the power of something that gives me 128. Okay, so in your calculator, we already know, let's see. So we can try 2 to the power, so this is trial and error. We're trying 2 to the power of 4, we get 16, too low. Okay, so then we go 2 to the power of 10. What's that equal to? 1024, too high, right? So we're just trying to figure out what answer will give us 128. So we know it's an answer between 4 and 10, probably closer to 4. So 2 to the power of, let's try 6. Okay, so if you get the number in one shot, awesome. If not, keep trying. So 2 to the power, I'm gonna go up 1. So 2 to the power of 7 is 128. So this is the number that I want to use now. So 2 to the power of 7 is going to replace 128. Okay, so what we're going to do is replace this little box with a 7 because this is 128. The reason we do this is called common base method, because if these bases on each side are equal to each other, we can ignore them because that means the powers have to be equal to each other as well. So if the bases are the same, we can ignore them and look at only the powers. So the 7 is equal to x minus 1. And then what we can do is solve for x. We can add 1 to this side, add 1 to this side, because we're trying to isolate for x. We're trying to get x by itself. So these guys cross each other off, leaving us with x equals 8 as our answer. So that means that we are on, therefore, we are on spot number or chess spot number 8. Okay, so chess spot number 8 would correspond to that. So if we continue the pattern, I can go above and check. So we know that here, if we continued the pattern and doubled it, it would be 32, then 64, and then 128. So I could have done that, but this is the mathematical way of solving for it. So this is called common base method. Okay, so we're going to be practicing that, but in order to continue, we need to review our exponent law. So I wanted to show you something here first to help review.
Learn about the laws of exponents. If you look up the laws of exponents online, check it out. Math book, you'll probably see a long list of equations that looks something like this. Wow, that's kind of overwhelming when you see them all at once. But don't worry, we'll take them one step at a time, and you'll see that they're not that
Let me just get full screen for you guys.
complicated after all. But before we get going, if you're not confident with the basics of exponents, I highly recommend watching our previous videos about them before moving on in this video. Okay, let's start with just the first two laws on our list, which should look familiar if you watched our video called Exponents in Algebra. They're just the two rules we learned in that video. You know, rules, laws, same difference. So you probably already know them. They simply tell us that anything raised to the first power is itself, and anything raised to the 0th power is just 1. And because we already know about exponents that are higher integer values, like x to the second, x to the third, that means we've pretty much got things covered, right? Ah, not so fast. Don't forget that integers can have negative values too. For example, what if we had the expression x to the power of -1, or -2, or -3? We know that exponents are a way of doing repeated multiplication. But how in the world could you multiply something together a negative number of times? Well, you can't. Fortunately, the next law on our list tells us how to interpret a negative exponent. That law says x to the negative nth power equals 1 divided by x to the nth power. And if you think about it, that kind of makes sense. A negative number is the inverse of its positive counterpart. And division is the inverse operation of multiplication, right? So a negative exponent is basically repeated division. X to the -1 would be 1 divided by x. X to the -2 would be 1 divided by x divided by x. X to the -3 would be 1 divided by x divided by x divided by x, and so on. Seeing it like this makes the pattern clear. But mathematicians prefer to express negative exponents in fraction form, where 1 is divided by the same number of x's multiplied together. But since those multiplied x's are all on the bottom of the fraction, you're actually dividing by all of them. Here's an example that will help you see that that's true. 2 to the -3rd power. Let's first try that as a repeated division problem like our pattern shows us. We always start with a 1, so we would have 1 divided by 2 divided by 2 divided by 2. If we do those operations from left to right using a calculator, we get 0.125 as the answer. Now let's write it in fraction form like our law of exponents tells us we can. 2 to the -3rd power would be the same as 1 divided by 2 to the 3rd power. And that's the same as 1 over 2 times 2 times 2, which simplifies to 1 over 8, and 1 over 8 simplifies to 0.125. See, whether you write it as a pattern of repeated division or in fraction form, like our inverse law shows, you get the same answer. And now you know how to handle any expression with a negative exponent. It's just 1 over the same expression with a positive exponent. X to the -1 is 1 over x to the +1, or just 1 over x. x to the negative 2 is 1 over x to the positive 2. X to the negative 3 is 1 over x to the positive 3, and so on. All right, 3 laws down, 5 more to go. And these next 5 show us how we can do various math operations involving exponents. In fact, the next law tells us how we can take a number raised to a power and then raise that to a power. As you can see, it shows an expression, x to the power of n, grouped inside parentheses, and then that whole group is being raised to the nth power. It's a nesting situation, kind of like those Russian nesting dolls. So what if someone asks you to simplify the expression x squared cubed, which means the entire x squared term is raised to the third power? Well, our law tells us that we can simplify that by multiplying the exponents together. See how it equals x to the power of mn, which means m times n? That means x squared raised to the third power would be the same as x to the power of 2 times 3, which is 6. Want to see why that's true? Well, think about what it would mean to raise x squared to the third power. It would mean multiplying 3 x squared terms together, like this. And each one of those x squared terms simplifies to x times x, right? So we end up with 6 x's being multiplied together, which is just x to the 6th power. See, our law works great. If you have a number raised to a power, and that's all raised to another power, you can just multiply the 2 exponents together to simplify it. And it works for negative exponents too. Like what if we had x squared raised to the negative third power? Well, our law tells us that that's the same as x to the power of 2 times negative 3, which is x to the negative 6th. To see if that's true, we'll need to use the law we just learned about negative exponents and rewrite this as 1 over x squared to the positive third power. That simplifies to 1 over x squared times x squared times x squared, which in turn simplifies to 1 over 6 x's being multiplied together. And that all checks out, because 1 over x to the 6th would be the same as x to the negative 6th power. Pretty cool, huh? Okay, we're halfway through our list of laws, and we're going to look at the next 2 as a set, because they tell us how we can multiply and divide expressions that have the same base. And that's important because we couldn't simplify them to have a single exponent if the bases were different. The first law says that if we have the base x with exponent m being multiplied by the same base x with exponent n, we can combine them simply by adding the exponents together. And the second law says if we have the base x with exponent m being divided by the same base x with exponent n, we can combine them simply by subtracting the exponents. Let's see some examples of each, like this one, 2 to the third times 2 to the fourth. Does that fit the pattern of our first law? Yep, the base of both expressions is the same, but they happen to have different exponents. The law would still work if the exponents were the same, but they don't have to be. Just the bases have to be the same. Our law tells us that this would equal 2 to the power of 3 plus 4, or 2 to the 7th power. But does it? Well, let's break it down and see. 2 to the third is 2 times 2 times 2, and that's being multiplied by 2 to the fourth, which is 2 times 2 times 2 times 2. That's a lot of 2's being multiplied together, 7 2's to be exact. Aha! So that is what you'd get by just adding the exponents together, since 3 plus 4 equals 7. And this law makes total sense if you think about what an exponent really means. The exponent is telling you to do repeated multiplication of the base, right? So this first part is telling you to multiply 3 2's together, and the second part is telling you to multiply 4 2's together. So that's why you can add the exponents together if the base is the same. Or think about it like this. If we had 10 x's all being multiplied together, we could form different groups of them and combine them using exponents. Like we could combine the first 4 x's into x to the fourth, and combine the remaining 6 x's into x to the 6th. And of course those expressions would be multiplied together since all of the x's were being multiplied. But you'd probably never want to do that, would you? I mean, why not just combine all 10 x's into the expression x to the 10th? But there you see that our law holds true. X to the fourth times x to the 6th would equal x to the power of 4 plus 6, or x to the 10th. Okay, now let's move on and see some examples of the second law in this set, which tells us how to divide expressions with the same base. Suppose we have the expression 5 to the third power divided by 5 to the second power. Our law says that we can simplify this by subtracting the exponents. Specifically, we take the exponent on the top and subtract the exponent on the bottom from it. If we do that, the simplified version would be 5 to the power of 3 minus 2, or 5 to the first power. But is that right? To see, let's write the expression out in expanded form. On the top of our division problem, we have 5 to the third, which is 5 times 5 times 5. And on the bottom, we have 5 to the second, which is 5 times 5. Does this look like something you've seen while simplifying fractions? Yep, since all the bases are the same, they form pairs of common factors on the top and bottom that can be canceled out. This 5 over 5 cancels, and this 5 over 5 cancels. If you don't know why that works, be sure to watch our video about simplifying fractions. And what do we end up with? Well, all the factors on the bottom canceled out, which leaves 1 since there's always a factor of 1. And there's only one 5 left on the top. So our expression simplified to 5 over 1, or just 5. Following our law, we got a simplified version of 5 to the first power, which is also just 5. So it really did work. But to make sure you've really got it, let's try using this law again with the expression x to the fourth power over x to the sixth power. This one's interesting. Our law says that we can simplify it by subtracting the bottom exponent from the top, right? But in this case, that will give us a negative exponent, because the bottom exponent is bigger than the top. 4 minus 6 would be negative 2. So according to our law, this expression should be equal to x to the negative 2. Let's try writing it out in expanded form to see if that's true. On the top, x to the fourth would be the same as 4 x's multiplied together. And on the bottom, x to the sixth would be the same as 6 x's multiplied together. Once again, we see that there are pairs of common factors that we can cancel. 4 pairs to be precise. And when we cancel them all, we're left with a 1 on the top, because there's always a factor of 1. And only 2 x's multiplied together on the bottom. If we recombine these 2 x's, we get 1 over x squared. And if you remember the law we learned earlier about negative exponents, you'll see that 1 over x squared is exactly the same as x to the power of negative 2. So these laws really do work. Okay, it's finally time to look at the last 2 laws on our list. And fortunately, they're pretty easy ones, so we're not going to spend too much time on them. These laws look kind of similar to the last pair. Just like before, the first one involves multiplication, and the second one involves division. But notice that in these laws, the bases are different, but the exponents are the same. That's the exact opposite of the situation with the last pair of laws. It turns out that these laws aren't about simplifying exponents. They're about how you can distribute or undistribute a common exponent to different bases. The first law shows this group, x times y, that's being raised to the power of m. And it says that you can rewrite it as x to the m times y to the m. In other words, you can distribute the exponent to each factor in the group. And the second law shows the group, x divided by y, that's being raised to the power of n. And it says that you can rewrite it as x to the n divided by y to the n. In other words, you can distribute the exponent to each part of the fraction. Of course, these laws would work in reverse too, and you could undistribute the exponents if they're the same. For example, if you're given the expression
Okay, so the only law that's not mentioned that I still wanted to include was the radicals. Okay, so square root functions. So let's say you had x and then you had this index here. So the index is that little number in front of your radical button or your radical sign. So this is your index. And let's say you had a value here, which is your power. So you can actually rewrite it as x to the power of your power at the top and your index at the bottom. So that would look like this. Let's say you had the square root of x to the power of 5. So that would be equal to x to the power of 5 over the index, if you don't see it, is actually a 2. So that means a square root function. So that means that it's going to be 5 over 2. So these are equal to each other. So that's the only rule that they didn't show. So I wanted to include that. Okay, so what we're going to do is we're going to use those exponent laws to simplify and get it so that there is a power on each side. So the same power has to be on each side and nothing else. So we're going to start off with 2 to the power of 1. 2 to the power of 1 is still 2. So we're trying to write every single thing as a base to the power of something. So 2 to the power of 1 is still 2. Then we want to get the same base for each of these values. So we're trying to get the same base for every single value. So we know that 2 to the power of 2 replaces 4. So it still means 4. Outside the bracket, you still want to write this 2x as a power. So you're going to write 2x. 1 is the same as saying 2 to the power of 0. 32 is the same as saying 2 to the power of, so you can try it with your calculator, 2 to the power of 5. So we know that 2 to the power of 6 is 64. So 2 to the power of 5, if you try that in your calculator, check that you're getting 32. So these mean the same thing. So all of this still means the same thing as A. It's just rewritten so all the bases are 2's. So there's a base of 2, base of 2, base of 2, base of 2. So that's your goal for each of these questions, is to have the same base. Now we're going to follow our rules. Our rules that stated that whenever you have a power raised to a new power, you multiply. So we're going to start with that one. So we're going to have the base of 2 raised to the power of 4x, because you're multiplying 2 times 2x. Whenever two bases divide, you're going to subtract the powers, versus here we multiplied. Okay, so it's going to be 2 to the power of 0, take away 5. Next, we're going to combine these powers. Whenever you have two bases multiplying, you want to add the powers. So it's going to be 2 to the power of 1 plus 4x, which is equal to 2 to the power of negative 5. 0 take away 5 is negative 5. Now, just like in the previous question, common bases. If you have the exact same bases on either side of the equal sign, you can ignore them. So that's our goal here. Our goal is to get a single base on the left side, a single base on the right side, because if that can happen, then what happens is our powers are then equal to each other. So we can ignore everything else around it. So now all we have to do is get x by itself. We are trying to solve for the variable of x. Okay, so we're trying to solve for x. So what we're going to do is we're going to subtract 1 on both sides of the equal sign. These guys cross each other off, leaving us with 4x equals negative 6. Next, we're going to divide both sides by 4 to get x by itself, which means that x equals, if you put that into your calculator, negative 6 divided by 4 in your calculator should give you negative 1.5. So that's our answer. Now it does say to verify, so we still want to check. We still want to go back to the original and see if left side equals right side. Okay, so what you should be doing is plugging it back in to see if left side equals right side. So I'm going to do that as well. You guys just wait till it gets set up here. Okay, so we're comparing the original question. So we're going back to the left side of the equation. Remember how it said 2 times, in brackets, 4 in brackets, to the power of, we have 2x. So instead of x, we're going to put brackets negative 1.5. So remember our x that we just solved for was telling us that x was negative 1.5. So I'm putting that and replacing it with the x. So that's the left side of the equation. Now you're going to compare it to the right side of the equation to see if they are the same. So you're going to put in your calculator 1 divided by 32. That's the right side of the original question. Do you guys see how they're equal? The left side, when I plugged in negative 1.5 for x, is the same as the right side of 1 over 32. So that is how I verify my solution. So I know that my answer is correct, so I can kind of give myself a check mark. That's my check. So that's by substitution. I verified. So that's what the question's asking you to do, is check your answers. The next question. I have a base of 5 here, which means that I have to get the other side to also have a base of 5. So the left side is going to stay the same. The right side, what I'm going to start by doing is writing 125. We're going to get rid of that square root. So remember previously I said that whenever you have the square root, you can change it to a power. So the power is 1 even if you don't see it. So there's 1 over. So whenever you don't see the index, the number in front of it, it's actually a 2. So it's going to be 1 over 2. So square rooting something is the same as saying 125 to the power of a half. So I'm going to just show you that these are equivalent to each other. So I'll prove that these are the same. So if I square root 125, and if I take 125 to the power of a half, they are the exact same thing. Okay, so you'll find that they are the same. They give you the exact same value. So these are equivalent. We're just rewriting it so it's a power instead of a square root. That's all we did here. So that's our first step. Second step, we want to get that common base. So we want to write 5 to the power of something that is equal to 125. So this is where you take your calculator and you say, okay, 5 to the power of, let's try 3. Okay, so you might get it on the first try. Sometimes you might have to try a few values until you can get the same value. So I know that 5 to the power of 3 is 125. Okay, so 5 to the power of 3 is going to replace 125. The 1/2 is still going to be there though. So we need to write 1 over 2. Next, we want to combine these guys. So these guys will combine by multiplying because it's a power raised to a new power. So we're going to multiply those two powers together. So the left side's still the same. The right side is going to be 5. And then in your calculator, you're going to take 3 multiplied by a half. So 3 multiplied by a half. Three multiplied by 1 over 2. So you can do this in your calculator and you should get that it's equal to 1.5. So since it's a number that ends, we can write it like this. We can write 1.5 instead. So we're going to write, instead of 3 to the power of 1/2, we're going to write 1.5. Now, remember how I said that when the bases are the same, the powers will also be equal to each other. So we can ignore the bases because they're identical on both sides of the equal sign and there's only one on each side. So you need to make sure there's only one base on each side. So now we just have to ignore the 5s and look at the powers. We know that x plus 2 has to equal 1.5. So let's get x by itself. So we're going to subtract 2 on both sides of the equal sign to get x alone, which means that x, if you put that into your calculator, 1.5 take away 2, you should get negative 0.5 as your answer. Okay, remember we're still going to verify. Verifying means plug this back into the original question and see if left side equals right side. So I'm going to go back here and I'm going to check to see if the left side of the equation equals the same as the right. Okay, so in your calculator, you should be putting 5 to the power of, remember how it says x plus 2? Instead of x, you're going to write negative 0.5 plus 2. So that's the left side, put equals. The right side was the square root of 125. So put the square root of 125 to represent the right side of your equation. You know you're doing this properly if both sides are equal to each other. So the left side is equal to the right side. So yes, that is the answer. Negative 0.5 is the solution. So we can put a check mark to show that that is correct. We just verified. Here, we want to get them both to be a base of the lower number. So in this case, the lower number is 3. We can write everything as 3 to the power of something. So this guy, this 3 is already good. This base is good, but we need to get the left side to also be 3 to the power of something. So 9 is the same as saying 3 to the power of 2. So we're going to write 3 to the power of 2 is 9. Outside, we still write this x minus 1. And then the right side is 3x minus 3. So the right side did not change. Next, what we need to be careful of right here is that these guys need to multiply. Okay, when they multiply, we have to distribute. That's the biggest thing that you need to remember is that that 2 needs to multiply by the x and the minus 1. So it's going to be 3 to the power of 2x minus 2 times negative 1 is negative 2. The right side stays the same. Okay, so what I did was I distributed the 2 to the x and the minus 1. So that's really, 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 really important. So to get this, I distributed. Distribute. So put a little star there to make sure that you don't forget that. Next, when the bases are the exact same on both sides and there's only one of them on each side, that's when you can ignore them. Because if the bases are equal, then the powers will be equal. So that's what we're trying to do, is ignore these guys and we're going to write that 2x minus 2 is the same as x minus 3. Now we need to bring the x's on one side of the equation and the numbers to the other side of the equation. So we always try to bring them to bring it to the side that has more x's. So I'm going to subtract x to cross these guys off on the right. So always do the opposite sign. So now you have 2x take away x. So 2x take away 1x is just going to be x. Next, we're going to add 2 to both sides of the equation to get x by itself. These guys cross each other off. That gives us x on the left, and then negative 3 plus 2 is negative 1. Okay, so what I want to still do is I want to verify my solution. I want to plug in x as negative 1 in my calculator to see if left side equals right side. So in my calculator, you're putting 9, so this is the original question, 9 to the power of. Instead of x, you're putting negative 1, and then it says x minus 1. So negative 1 minus 1. That gives you the left side of the equation. Now you go to the right. 3 to the power of negative 1 minus 3. Negative 1 for x, and it says minus 3. Put that in your calculator, and you should see that the answers are identical. If the answers are identical, that means that you're good. Okay, so we just checked, and this negative 1 is the solution. So that is verifying. Okay, so that is called, what we just did was called common base method. Okay, so common base method. I want you guys to look at example number 2 and determine, can you get a common base here? Okay, so if you're looking at 3, 2, and 5, these bases cannot be made to be the same. 3 to the power of something will never equal 2. 2 to the power of something will never equal 3. 2 to the power of something will never equal 5. Like, there's nothing that would work that would make all of them be equal to the same base. So we cannot use common base method. Can't use common base method. So common base method cannot be used in a situation like this. So the method that we're going to use is we're going to use the graphical method. Okay, so this can be always used. So we're going to graphically solve for the answer. Okay, so to solve graphically, what you're going to do is you're going to put the left side of your equation into y1 and the right side of your equation into y2. So y1 is the left side, y2 is the right side. Okay, so our left side of the equation, we're going to put 3 to the power of x minus 5. And the right side is 2 multiplied by 5 to the power of x over 4. Okay, so let's start by putting that into our graphing calculator. So you're going to start by pressing y equals. In y equals, you're going to clear whatever is there. Okay, so you need a clean slate. So in your graphing calculator, you want to make sure you're at y equals. and you want to make sure that everything is clear. You want to put the left side of your equation into y1. So you're going to write 3 to the power of, here's my power button. If you have an older style calculator, you're going to need brackets. If you have a newer style calculator, you will not. So just to be safe, for the older style calculators, make sure you put bracket x minus 5. So that's the whole left side of the equation. Then under y2, you're going to move your arrow down till you get to y2. You're going to enter 2 bracket 5 to the power of, and again, if you're using an older calculator, put a bracket around your power. So bracket x divided by 4. If you have a newer style like I do, 84 and up, you don't really need the brackets. It will keep it as a power, so it's okay. So older style calculator, brackets. Newer style, you don't need the brackets, but this bracket will kind of work for everyone. So as you can see, the left side went into y1, the right side went into y2. The difficult part right here is to figure out a window that would work here. So we have to figure out, remember, exponentials grow very quickly. We have to figure out where are we going to see an intersection. So what I'm going to do is I'm going to keep the standard window for now and see if there is an intersection between these two graphs, my blue graph and my red graph. Blue, red. Okay, so I'm going to go to the window. There's my standard window that I normally use. Okay, so make sure your window is -10, +10, 1, -10, +10, and 1. So this one is the standard window. You're going to see that we're going to have to adjust it because once we graph it, so you're going to press graph. So press the graph button. Okay. So as you can see up here, they're not intersecting yet. So we need to see more of this. We need to go up here and figure out what that means. This is your y minimum. This is your x's. We don't need to see the left or right side. We need to see more up. That's called your y maximum. So we need to make our y maximum larger. So what you're going to do is you're going to go back to your window. And instead of our y max cutting off at 10, let's make it larger. Let's maybe try 50 and see if that helps us. Okay, so it's all about just finding what value is enough to see that intersection point between the two different graphs. So you're going to go over to your y max. Clear whatever's there, and let's put it to 50 for now. Let's see if that's enough. Now, you can already graph and see if it's going to intersect. So let's graph at y max of 50. So now, in order to see an intersection, in order to actually get the intersection, you have to be able to see it. So we're so close. We're so close, but that was still not enough. So we want to retry and go to our y max. Let's double it again. So to be sure, I'm going to go down and to y max and change it from 50 to 100. Okay, so adjust it to be 100 instead of 50. And then this should work. So it's sometimes about trial and error. So I'm trying to show you that, if you don't see an intersection, then try again adjusting your window until you do see it. So in this case, I had to adjust my y maximum. Okay, finally, so now I can see an intersection. Once you see your intersection, you're going to press second trace. So second trace. So that will take you to this menu right here, and you should be pressing number 5 where it says intersection. So you're going to press 5 and then enter. Okay, so what happens from there is once you get to your steps, what you want to do is you want to move your cursor left or right. You want to, in this case, move it, in my case, right, until you get as close to your intersection as possible. So you're going to move that little kind of bug, that little move tracer. And you're going to move it left or right. In my case, I'm going to move it right. Once you get as close to the intersection as possible, you're just going to press enter 3 times. Mine's just really slow, but once you get as close to the possible, so you want to move your cursor about here, and then you want to press enter 3 times. So when it says guess, press enter again. So you're just pressing enter 3 times from there, and it should give you the intersection. So your intersection will always be the x coordinate. So in this case, they're asking you to round to 1 decimal place. So I have 8.885, which I'm going to round to 8.9. So always round to whatever they tell you to. So I'll just write down the rest of my steps here. So once you set your window, you're going to write down what your window is. My window was -10 for x, +10 for x, and then 1. So that was my minimum, maximum, and scale. This went from -10 to 100, going up by 1. This was my y min, my y max, and my scale. So you're trying to show me what you did to get your answer. Once you graphed it correctly to see the intersection, you had to press second, trace, number 5. Once you press number 5, you're going to have to go as close to the intersection, move to intersection, and then press enter 3 times. And what that should have given you is the x coordinate. So as you can see in the original, it's saying x is missing. So we only needed to solve for the x, not the y. So don't give me both. So your answer was 8.885, etc. But we need to round to 1 decimal place. 1 decimal place. So that means our answer should have been 8.9. Okay, so make sure you're able to do that. Okay, so once you have this written down, make sure you guys can pause. You can pause this video if you still need to copy this down. But what you want to do right after you finish this question is you want to try some homework questions just based off of these. So today we're going to work on just numbers, just equations, no situations. So this is your last example. And I want you to go to the homework list, and I've highlighted which ones you need to do. So from day 1, you should be able to do all the questions. So that's what you want to do is practice now, day 1 and day 2. Start with day 2 because that's the freshest in your mind. So start with day 2, and you should be doing from day 2, 4DF, 5C, 7DF, and 8D only. And then tomorrow you'll do the remaining ones after we do the word problems. Okay, so start with day 2, start with those 4 question types, and then go back to day 1 and fill in the rest of the questions. Okay, so tomorrow we're going to continue on with 6.3. Okay, I hope that helps. Email